Hello. In this video we're going to be talking about abstract vector spaces. And in particular we're going to be looking at a few examples of abstract vector spaces that I think are important and we're going to be using later on in the term. So to start out with, let's look at this first abstract vector space we're going to call P. It's a fancy curly P and it is the set of polynomials. Okay? So just a constant term plus a linear term plus a quadratic term, etc., up to a degree d term. All the coefficients must be real. Again, we could use complex numbers here, but I'm going to stick to real numbers just for this example. In particular, P is a real vector space. And d here can just be any natural number. That's the degree. Okay. There is one special case where we want to not say that d is the degree, and that is for the zero polynomial. Some people like to define the degree of the zero polynomial as negative infinity. In practice, for what we're doing, it won't really matter what we call the degree of the zero polynomial. It is the only polynomial that's weird, and so we'll just kind of ignore that case when talking about degree. Okay, so this is the set of polynomials in the variable x with real coefficients. And if you take another algebra class beyond linear algebra, you might see it written like this, r of x. And of course the r can then be replaced with any other thing you want, and the x could also be replaced with any other variable you want. Okay, so we're also going to define, in addition to this p here, we're going to define this p sub d. And these are going to be specifically the polynomials in P which have degree at most d. Okay? And no matter what d is, this is going to include the zero polynomial. Okay? And the reason we care about this is because of this proposition here. Both P and P sub d for any value d are going to be vector spaces. So, how might we go about showing this? Well, these two things, P and P sub d, are vector spaces for different reasons, or at least we're going to show that they're vector spaces using two different sets of reasoning. So remember that to show something is a vector space, we have to go through this huge checklist on at the beginning of section 4.1. So this is a 10-item checklist. And to start out with, we need to note that we can add two vectors, in other words, add two polynomials together, or scale. We also need to be able to scale those polynomials by a constant. So constants in this case are real numbers. Okay. The first item on the checklist is you can add two polynomials together to get another polynomial. That should be pretty clear. The second item is if you add two polynomials, that's the same thing as reversing the order and then adding them. You get the same result. Okay, the third item is associativity. All of these things work for polynomials just as well as they do for any of the other vector spaces we've looked at. So I'm going to not go through this whole list, but instead I just want to point out this is a long list to go through, and we don't want to have to go through it every single time. So for P sub d, we're going to do this in a slightly different way. We're going to use the fact that we already know P is a vector space by going through that list of 10 items. And there is a much shorter list that we can go through for P sub d because P sub d is a subset of P. So because P sub d is a subset of P, we only need to check three things. We need to check that the zero polynomial, which I'm going to write as a zero vector, because we're thinking about all these polynomials as vectors. We need to check that that is in P sub d. That's the first thing we need to check. We need to check that if P and Q are two polynomials, in P sub D, then their sum is also in P sub D. And finally, if P is in P sub D and lambda is in R, sorry about the handwriting here, it's very difficult to write on the bottom of the board, then lambda times P is in P sub D. Okay, so we need to check that it's closed under scalar multiplication and addition, and we need to make sure it's not empty. In other words, the zero vector is in there. Okay, so as long as we check these three things for P sub D, and we already know that P sub D is sitting inside of another vector space, that is all we need to check to make sure that P sub D is a vector space itself, okay, because it is a subspace of another vector space. Okay, so hopefully these three facts are obvious for polynomials. Right? If you add two polynomials which are at most degree d, you get another polynomial of degree at most d. 0 is a polynomial of degree at most d. And so 0 is the polynomial that you get from setting all the coefficients to 0. And if you scale a polynomial of degree at most d by a real number, just multiply all the coefficients by that number lambda, and you get another polynomial of degree at most d. Okay, so that proves this proposition. So we're now going to look at a couple of questions here. So this first question says, what is the dimension of P3? Okay, so the dimension of P3 is determined by the number of elements in a basis for P3. So the answer for this is going to involve writing down a basis. So let's just say this basis here. So there are many bases that we could choose, but this is sort of the standard easy one to look at. 1x, x squared, and x cubed. And this is sort of the natural choice because literally the definition of P, and therefore P sub D, uses the vectors 1x, x squared, and x cubed, and writes the set P as the set of linear combinations of those vectors. Okay? So we're stopping when d is equal to 3. So our highest power of x is 3. And we get 4 elements of our basis. Okay, so this is definitely a spanning set just by the definition here. The set of linear combinations of these things is spanned by those things. And it's also linearly independent. The way we can tell that is just via former knowledge of polynomials that you should have. If you add some linear combination of, say, 1x and x squared, if you just add a bunch of those things together, possibly scale them up a bit before you add them, there's no way to get to x cubed. So x cubed is not in the span of these other three things, and similarly, none of them are in the span of the other ones. Okay? You have to do some multiplication to get to the other ones, which is not allowed. You can't multiply two vectors together. Okay, so this is a basis, so the answer to this question is the size of this thing so the dimension of P3 has to be 4. So 4 is our answer. All right. This next question says, which of the following are subspaces of P? So just to note, all of these four sets that I have written here, A, B, C, and D, they are all subsets of P. And you can tell that immediately by just looking at the first part of this before the bar that says I'm only looking at the polynomials in P. Okay? In particular, I'm looking at polynomials. And so all of these are subsets of P. Therefore, I only need to check these three items. Okay? So the easiest one to check is this one that says the zero vector is in there. So to check that, I'm just going to run through all four of these. And the first one here, we can see right away the zero vector. If I say that P is the zero polynomial and I plug 2 into it, well, it shouldn't matter what I plug into the zero polynomial. I should just get 0 out. And in particular, that's not going to be 3. So the set of polynomials where P of 2 is equal to 3 does not contain the zero polynomial. Okay? So since the zero vector, the zero polynomial, is not in the set A, the answer is no. So I'm just going to put a red X there. Okay, so if you look at the rest of them, the zero vector is in the rest of these. So zero vector evaluated at 5 is 0. If you add zero vector evaluated at 1, zero polynomial evaluated at 1, plus the zero polynomial evaluated at 2, that's 0 plus 0, and that's the same thing as the zero polynomial evaluated at 3. Okay? And just a note over here, if you plug 0 into the zero polynomial, you're going to get 0, and that is not equal to 1, so D is also fine. Okay, so the rest of these things satisfy this first property. So we already know that A is not a subspace, so we don't need to check anything else for A. It's automatically out for this. We do need to check these other items, though. So these other items say that if I add two polynomials, P and Q, in these sets, I should get another polynomial in the set. So let's see if that's true. Okay, so I'm going to start out with B. So the set B is the polynomials such that when I plug 5 into them, I get 0. And if I take two of those polynomials, so let's say P and Q are in B, I'm going to use a little bit of a shortcut here. I'm actually going to check both of these things at the same time. So P and Q are in B, and lambda is in R. And the way we're going to check both of these at the same time is I'm going to check that P plus lambda times Q is in B. Okay? And you should be able to reason out that if all polynomials of this form are in your set and the zero vectors in the set, which we've already checked, then all three of these items must be satisfied. Okay, so I'm going to go ahead and check that. So if I know that P and Q have this property such that when I plug 5 in, I get 0, then when I plug 5 in to this more complicated polynomial, P plus lambda times Q, I should get, just by definition, I should get P of 5 plus lambda times Q of 5. And that's a plus sign. So P of 5 plus lambda times Q of 5. Well, P of 5 must be 0 since P is in B. So this is 0 plus lambda times Q of 5 must also be 0. And 0 plus lambda times 0 is 0. So we've checked that if you take this polynomial, you plug 5 into it, you get 0. Therefore, we're in this set. And that means that it's closed under both addition and scalar multiplication. By the way, this is closed under addition by taking lambda equal to 1. That's literally P plus 1 times Q, or P plus Q. And it's closed under scalar multiplication by taking p equal to 0. Since we know the 0 vector is in here, we're allowed to take p equal to 0, and then we just have lambda times q. As long as q is in there, then lambda times q is in there. That means all scalar multiples of anything are in there. Okay, so we've checked everything for b. That means b is a vector space. I'm going to put a green check there for a yes. Okay, so on to C. So again, I'm going to pick P and Q and C. And lambda and R. And we want to check to see if this property is going to hold for P plus lambda times Q. Okay, so P plus lambda times Q evaluated at 1 plus P plus lambda times Q evaluated at 2 and hopefully, just put a question mark here, that is equal to P plus lambda times Q evaluated at 3. Now I'm not going to write this whole thing out, but this is a true fact. You get this from distributing the 1 in, similar to how we distributed the 5 in here, and then distributing the 2 in here, and grouping the 1s together, and then grouping the 2s together, and then sorry, the 1s and the 2s are already grouped. Group the p's together and then group the q's together, factor out the lambda, and you should get exactly this. Okay, you have to use this fact for both p and q in there. So I'm going to leave it at that and just say this does work. This is a subspace of p. Okay, on to part D. So this set D has an inequality as opposed to an equality, and that should be a red flag. So it turns out D is not a subspace of P, and one quick way to see that is if you just reason out that, okay, say you take two polynomials that at 0, in other words, the constant term, it's the same thing as what you get when you plug in 0 into a polynomial. If the constant term of p is not 1, and the constant term of q is not 1, and you add those two together, is it possible to get to 1? Well, yes it is. So there are two numbers which neither one are 1, that add together to be 1. Okay, so we just need to come up with an example of that. Okay, and my example is just going to be really basic polynomials, constant polynomials, and I'm going to let p equal 3 and q equal -2. So these two constant polynomials both satisfy this condition. If you plug 0 into them, well, this first one's going to give you 3, and the second one's going to give you -2. Neither one of those things are equal to 1. Therefore, these are both elements of D. But if you add them together, so these are both in D, but P plus Q is equal to 1. Okay, so it's the constant polynomial 1. In particular, when you plug 0 into it, you're going to get 1, which means this is not in D. You're not allowed to be 1, or you're not allowed to have a constant term 1. Okay, so that means that D is not a subspace. All right, so we have some more examples of abstract vector spaces here, or just vector spaces. And before I go into what each one of these things is, I want to cover some notation that you should be familiar with. So this is function notation. So name of the function, then a colon, domain, arrow, codomain. Codomain is another name for the range. It is the set of possible output values. So that is to say that not everything in B has to be the output of the function for some element of A, but B is the set of things that could be hit by the function. Okay, so this first set that we have here is the set of all functions from this set to this set. This set is the closed interval from A to B. So A and B are real numbers with A less than or equal to B. So we have the ability to scale these functions by scaling their outputs. So in other words, if I wanted to take lambda times f, this is the function, so lambda times f is the function which when I want to plug an x into it, I get lambda times f of x. Okay, so lambda times f is another function, and notice that if f of x is a real number, then lambda times it should also be a real number because lambda is a real number. Very similarly, we can add two functions together. This works the same way as it does for things we've previously seen. So the function f plus g with x plugged in is just f of x plus g of x. And this is again a real number plus a real number, making a real number. So when I scale a function or add two functions together, I get another function of this form. Okay, there's also a bunch of other things to check to make sure that this space is a vector space. I'm not going to check all of those things, so you can just believe me or you can check them yourself. Okay, so this next set is the set of continuous functions, again from the closed interval AB into the real numbers. So this is a subset of this, right? So it just has an extra condition on it that the function also has to be continuous. And that means that in order to check that this is a vector space, we just need to check that it's a subspace of this, which means there's only three things to check, right? So the first one is that the zero function is in here. Well, the zero function is continuous, so we're good there. The next thing is we need to check that if we scale a continuous function, it is still continuous. That's true. Hopefully you remember that from calculus. And similarly, hopefully you remember from calculus that if you add two continuous functions together, you get another continuous function. Okay, this third set, again, is a subset of this original set here. So we just need to check that in order to check that it's a vector space, we just need to check that it's a subspace. It is also a subset of this set because every differentiable function is also a continuous function. And if you recall from calculus, if you scale a differentiable function, then its derivative just scales. In particular, its derivative exists, which means the function is differentiable. And if you add two functions together that are differentiable, the result is differentiable because their derivatives just add together. Okay, that being said, the fact that I just stated is the statement that this operation, d dx, which is a function from the set of differentiable functions into the space of all functions on A to B. This operation on this vector space is linear. Okay, so I'll just restate what I just said. If you take the derivative of a scaled function, you get the scalar times the derivative of the function. Okay, and if you take the derivative of the sum of two functions, you get the derivative of the first one plus the derivative of the second one. Okay, so this operation d dx is linear. Okay, and I won't write down this next one. Before I go on, we're getting general functions here just because the fact that you take the derivative of a function doesn't mean you're going to end up with something that is again differentiable. You could start out with something that has a derivative, take a derivative, and then you're left with something that doesn't have a derivative, and it might not even be continuous. But those are weird edge cases from calculus. I don't expect you to know all those, but at the very least you're going to get some function, and that's all we really need for this. Okay, so one more function, which is just this. And so I'm going to write this like this. I will call the function I, and we'll say that it goes from the set of continuous functions, which are all integrable, into the set of we'll just say general functions for now. And the map is, so the function, what it does is it takes an f here, and it sends it to, by the way, if you're not familiar, this little mark here that I put at the beginning of the arrow is just saying what happens to one particular element of this set. So if there's no mark there, I'm saying elements from this set go into this set. If there is a mark here, I'm saying this particular element goes to this particular element. And where I'm going to send it is, so I'm going to write this as f of x, just for clarity. I'm going to send this to the integral from 0 to x of f of t dt. So t here is a dummy variable. This whole thing ends up being a function of x, so we are still in this space. Okay, I will also note that, so this is linear because integrals act linearly. So you can integrate the sum of two functions, and that's the same thing as integrating the first one, integrating the second one, and adding the results together. Scalar multiplication works just the same. This function, according to the fundamental theorem of calculus, actually has a nice derivative. The derivative of this function is just little f of x. And so I can actually say, instead of this, if I want, I can change this to d, because I know the result is differentiable. So I know that it actually lies in this subset of that space. All right, thank you for watching.